Okay. Welcome everybody to ICTS Baroclinic. And it's my pleasure to introduce Professor Krishnendu Sinha from IIT Bombay. He is currently a professor there in the Aerospace Engineering Department. So he did his PhD from IIT Kanpur in 2001.
BTech is IIT Kanpur.
Yes, IIT Kanpur. And then he moved to US and to University of Minnesota and his masters and PhD, and then he did a couple of postdocs. And then he joined IIT Chennai as an assistant professor in 2005. And then there he spent 1 year, and after that he joined IIT Bombay. His interest, research interest is high-speed flow in aerospace applications, and also theoretical and numerical developments in fundamental flows, fluid flows. And in this field, he has made several important contributions, and because of that, he has been honored several selections. He is a member of American. He was a member of American Physical Society, and also is a member of the American Institution of Aeronautics and Astronautics. And he is an elected member of the National Science Academy of India. So, Professor Sinha will talk about sockets and turbulence and applications. So, please.
Okay. Thank you so much for that nice introduction, and thanks for coming. In fact, I'm very happy to have this invitation from ICTS for the colloquium. I come here last January, and I was very impressed with the kind of community and environment and the people I saw here. It's a good opportunity to come back and talk about what we do. As Anupam said, our main research is in the area of high-speed flows, mostly in aerospace applications. And lately, our focus has been on shock waves and turbulence. That is the topic of my talk today. And I've been told that the audience possibly is a bit kind of general. So I will start with very basic, simple things. So please bear with me if you already know it. And try to build it up from kind of the first principles up to the point where we can show some interesting results, some interesting things. It's interesting, I would kind of try to convince you that it is really exciting and interesting things we can do with fluid mechanics when we come to space and similar applications. In any case, if you find something which is not clear, please feel free to stop me anytime. I'll be happy to. It's okay to cover less, but to cover it well, I would say. Okay. This is a very basic slide. I think the picture on the left has not come out very well, but we are trying to introduce shock waves. With this small cartoon, it says that if you are flying, so the cartoon of an aircraft flying at subsonic speed, the speed of sound Mach 1, or supersonic speed, and it shows the sound generated from that aircraft radiating outward in the medium, in the atmosphere. And depending on what speed you are at, subsonic speed, you have a pattern like this. At sonic speed, all these sound waves tend to coalesce. And at supersonic speeds, they form what's called a shock wave. So Mach number greater than 1 is associated with shock waves, supersonic, hypersonic, which is Mach greater than 5. And shock waves are known to generate high pressure behind them, high pressure and high temperature. Air goes from ambient conditions to high pressure and high temperature conditions behind the shock wave. So the aircraft feels this high pressure and high temperature environment. This can lead to high loads in terms of drag and lift and other things. There can be high heat transfer, and some of those are our concerns when we deal with aerospace applications. I'll come to these things over and over and how it makes a difference in our research and what we can do about them.
What's one kind?
Yes.
What do you mean by behind?
Behind, that's a very good question. When we are sitting on the aircraft, let's say the aircraft is flying, the air ahead of us, which is not far away from us, is ahead, we say. And when it goes through the shock and comes to us, we say behind the shock. Yeah, that's a good point, because we keep using this all the time. Behind the shock is the flow that has passed through the shock, which has high pressure, high temperature. Okay. So, technology, engineering-wise, shock waves are a major challenge many times. How to handle them in supersonic, hypersonic type. That's one part of the side of the story. The other side is turbulence, which is something which we are probably more familiar with on basic fluid mechanics side. It is actually a very challenging problem because of its range of length scale, time scale, and the complexity of fluid mechanics and nonlinear behavior. And it has defied solutions for many, many decades in engineering. The interesting thing is that we look at the situation where turbulence and shock waves come together. And a picture like this is what I try to show. What we have here is this gray sheet is like a shock wave. Shock waves are generally thin regions in the flow where these it's like a discontinuity as it's called. So in this case, the shock waves are is visualized as a simulation in which the shock wave is visualized in terms of this gray sheet of I think it's density gradient or a pressure gradient. And then what the others, these the small things are the turbulence eddies that are passing through the shock wave. So we looked at a problem where turbulent flow goes through a shock wave. And the question is that what happens to turbulence, which is somewhat visible in the picture, the turbulence becomes much more vigorous when it passes through a shock wave. The eddies and vortices as we think about turbulence become stronger and the fluctuations are larger. There can be new kind of fluctuations generated, like some entropy fluctuations and temperature fluctuations, which possibly were not there before. So the question that we try to answer from very basic fluid mechanics is what happens to turbulence? How does its nature change? How do the scales change? How do the intensities change? And the related question is what happens to the shock wave? The shock wave also doesn't quite remain the way it was if it was uniform, nice, simple flow going through it. The shock responds to the turbulence by becoming unsteady and oscillatory, and in extreme situations, it can also break. It turns out that this problem, what we call a shock-turbulence interaction, is important role in many scenarios. So we will first look at this as part of this presentation talk, that we look at what's the physics happening inside this and how it affects this engineering applications or scientific things in nature as well. Okay, let me start with the engineering application. What I'm showing here is a slight variation of the last slide. Now we are talking about, this is like a plate on which there's a flow going over it. The flow is from left to right. And what we're showing here with these small things and eddies and vortices is the turbulent boundary layer that develops on the plate. It's a very common scenario in many aircrafts and aerospace vehicles. Flow over a wing, over a fuselage, can have things like this. When it is supersonic flight, it's possible that shock waves can be generated and shock waves can impinge on that plate. In this situation, what we're seeing is shock wave coming in, impinging and reflecting off from the example is here. We're talking about a rocket with external boosters, which is generally we have rockets for heavy lift, lifting heavy satellites. Each of these rockets or these will generate their own shock waves. It's possible that shock waves on adjacent booster rockets, smaller rocket, can impinge on the main rocket. So the situation is, although we can't visualize it in this image, it can be something like this. A shock wave coming from there is hitting here, a cartoon shown here. This is the main rocket body where the turbulent boundary layer is there, like what we have shown here. And a shock wave from an adjacent part of the vehicle can come and reflect on. It turns out that these points of impingement are crucial for designing this is a heat shield. A shock wave can generate high heat transfer where it impinges.
So this shock wave is in density gradient?
A shock wave is a gradient in density, pressure, and temperature. Mainly these are three things we look at. So when we show a shock wave, it's not visible to naked eyes, but if you have ways to image the density gradient, which are Austrian images, you can actually see them as part of, you can see them in an experiment to conduct in the wind tunnel.
So it was actually done when Elon Musk actually launched this Falcon 9, I think.
Okay.
So the atmospheric conditions were good enough that the shock waves were actually seen. Yeah.
It can happen. That's actually a very good observation. Because if you, there are certain conditions in which shock waves can be naturally visible, which are very few. It depends on the right combination of moisture in the air and the pressure and temperature. In fact, a simple search of shock wave on YouTube will probably show you some of those examples. In fact, an aircraft, when it crosses the sonic speed, there's some kind of a burst of water vapor which shows a shock wave. So there's only very few situations when you can see it. Many times you need special equipment to see it. An experiment, for example. Thank you. So we're talking about situations like this where turbulence and shock waves interact on, for example, a rocket, or for that matter, many other scenarios in aerospace applications. And there can be high pressure load, high heat transfer, and our job now is this can be understand the physics and predict these things. Can we predict how high the heat transfer would be so that person who is designing this part of the rocket and the outer covering can account for it? Because maybe somewhere right inside where the shock impinges would be the liquid oxygen tank, as people from ISRO tell us is possible. So they have to be doubly careful if they want to house sensitive instruments or fluid tanks inside. Okay. The next slide is a bit more general. Shock waves and turbulence come together also in applications of nuclear fusion and in supernova explosions. Again, these are not my area of research directly, but I thought I'd put these up for a bit more of interest from scientific community. It says that when supernova explosions happen, there's a shock wave that goes out, and how that shock wave interacts with the turbulent kind of things in the medium decides a lot about how the supernova develops and what kind of features it has. For an internal confinement fusion, generally the fuel, which is a very small pellet, is actually empowered with lasers so that we can generate a shock wave to compress it and ignite it. That's the way they work with it. Again, there's turbulence there actually helps in mixing and burn it faster and ignite it faster. So some of those things are also related to shock turbulence interaction and other physics as well. Alright, so with those two slides of introduction, application, let me define the problem, which we have in terms of what we call as a canonical shock turbulence interaction, where we have the simplest possible scenario where this interaction can take place. So we can imagine a situation where we have a field of homogeneous isotopic turbulence going through a shock which is initially just a plain normal shock. There are different kinds of shock waves for those who are new to it. A normal shock is possibly the simplest kind of shock wave. So we start with the normal shock, a uniform mean flow which is supersonic, and it becomes subsonic, less than Mach 1 behind it. And U1, U2 are then used for the upstream and downstream mean flow velocities. It may come up again later on. And I'm defining this problem in terms of a field of turbulence which has only velocity fluctuations. Again, we are kind of keeping temperature, density, other fluctuations aside, keeping it to bare minimum turbulent eddies, vortices, velocity fluctuations. Going through a shock wave, and it gets energized and its nature changes, whatever. And the idea is, can we understand what happens at the shock wave and can we predict what happens behind the shock wave? And this forms the framework of our the basic problem that we want to tackle, which itself becomes complicated as you would see. And if you can understand this problem and learn from this problem and see, can some of those learning help us in predicting the real life things. That has been kind of the motivation of our research. Okay. A few background kind of work. This canonical shock turbulence interaction has been studied quite a lot because probably of the simplicity. All the experimental works have been very limited because it's not easy to generate things quite in a controlled way in an experiment. There have been a few, very few work. Majority of the research has been in direct numerical simulation, where you would actually simulate the turbulence in all its nonlinearity and three-dimensionality, and then pass it through a shock wave and study what happens to it in all detail. So a direct numerical simulation would solve Navier-Stokes equation for a full range of length scales, as we call it, and try to not make any assumptions about the turbulence, or not try to capture all the scales of turbulence.
Just to be precise,
Yeah.
it's compressible.
It is compressible, absolutely. It's compressible Navier-Stokes equation. In fact, you're right. Sometimes we forget to tell ourselves, but we are solving. I'll come to that a bit more as we're solving compressible Navier-Stokes equation for this problem. So, among all the works that have been, we kind of identified three major groups, and I'm sure there are many more things we may not have included. But initial work was in the area of how much turbulence gets amplified, across the shock. So there was a series of works from Stanford in the 90s, which looked at can we do DNS and kind of study what's happening to the turbulence, how it is getting amplified across the shock. Then there was a series of work again from Stanford, which looked at more at the details of the turbulence, how is it from isotropic turbulence, how it became anisotropic, and what happened to the shock wave. There were cases reported by these authors where the shock was kind of broken, some holes were created in the shock wave and things like that, a bit more advanced things. And then there have been a group from Los Alamos who have been mostly interested in the mixing generated by the shock wave. So a shock, when it enhances the turbulence, it also enhances turbulent mixing, turbulent heat transfer, all kinds of things. These are three kind of the major contributions we see over the years, and then many more smaller things have been studied using direct numerical simulation. The other direction of work has been using theoretical analysis, where you can actually simplify this problem into a manageable set of, a manageable framework where you can actually solve it by hand. Of course, you can only solve one case by hand, and then you write a small computer program which can solve any of these cases by hand. So it's a fairly manageable task if you do a bit of theoretical analysis. And I'm going to go more over this a bit later. But some of the basic ideas the basic ideas were introduced almost in the 1950s and 60s. But then in the 90s, they were developed into a framework where turbulence and shock was effectively studied using this analysis. And there will be more work from the Spanish group, and we have done quite a bit of work in this area using the theoretical analysis to study and understand shock turbulence interaction. Okay, so before I go to the theoretical part, I'm going to give you a brief idea of what the problem is like when we're doing numerical simulation, and what we learn from it, and how we use the information. Now, we are looking at homogeneous isotropic turbulence going through a shock wave. So we set up the problem in a domain which is periodic in if you think about y and z direction, and in the x direction we place a shock wave. This wave is kind of a sheet, if you think about. We generate a box of turbulence, compressible turbulence, and make it pass through it and study the turbulent characteristic and statistics after the shock. Of course, it's easily said than done. First is that you have to handle the boundary conditions in the post-shock direction, which needs to be non-reflective, and so it doesn't quite disturb or contaminate your results where you want to study it. And the other problem in this is that the shock wave needs to be stationary in one place, and we need to do some amount of what's called back pressure control. Again, somebody in the will get to that. And once we have set up this problem, then if you look at this from a more from a physical point of view, we have like three parameters to control. One is the shock wave itself. How strong is the shock wave? That is determined by the Mach number of the flow. If you think about a Mach 1.5 or 2 or 2.5 flow coming towards the shock, and the shock is stationary. The shock Mach number is a parameter which people have studied over quite a range. It has to be greater than 1 because less than 1 subsonic flow, there is no shock wave. The second parameter is how strong is the turbulence. So how strong is the shock, how strong is the turbulence, how intense is the turbulence. That is determined by a similar quantity. If you take the turbulent fluctuation in velocity and define a Mach number out of it, that determines how strong is the turbulence relative to the shock wave. Again, these parameters vary over a quite a range to see how it will change the physics and the outcome of the interaction. And the third one is Reynolds number, which determines what is the viscous effect like. And here we have looked at, well, we meaning the overall community in general, in the range of 35 to 75, because DNS as we have it, higher the Reynolds number, higher the computation cost. So a simulation in this range of Reynolds number, and for these Mach numbers, can go up to grid points of 100 million points, and it can actually last for weeks if you have to look at it.
So this turbulence Mach number is based on the fluctuation after subtracting the average, right?
Exactly. Yes. Yes. Yeah. So turbulent Mach number is velocity fluctuation, RMS velocity fluctuation, which is after you take out the mean, and then divide by the speed of sound, which is mean speed of sound. Yeah. In some ways, we're trying to quantify how big are turbulent fluctuations relative to the mean flow. Yeah.
So, what this Taylor microscale Reynolds number would translate to in terms of the geometry of the box?
Let's see. It's a good question. I have to remember those numbers. I think it is taken in terms of the box size is, I think, 2 pi by 2 pi in the cross section, and it is non-dimensionalized by the most energetic gate number. So, in terms of, I'll have to really work it out. Sorry, I don't have the right number. Yes.
How good an approximation is the shock front to the stationary?
Good question. In fact, how good an approximation it is that the shock is really stationary. So nothing can be really perfect. That's what the point is, right? So we have to make sure that the shock is not moving too much during the course of simulation. First check, because you are collecting statistics, so the shock should not come into the domain where you're collecting statistics. Second thing you have to check is that if the shock has a finite velocity, even a small velocity, how big is that velocity relative to the flow coming in? So we generally keep it within 1% or so.
But in real life, is
Right. What is it in real life? In fact, very interestingly, in real life it is very hard to get a situation like this. It's a very kind of a model problem for isolating some of the physics and what is happening at that. In real life, many of the shock waves that we see in real life are oblique shocks, and you have to have something that generates a shock wave. An obstruction in a supersonic flow would generate a shock wave. So in that sense, this is an artificial situation where you're imposing a shock artificially without any obstruction. This flow is periodic in all directions. So what I'm trying to say is that in real life, the shock can be stationary if it is, let's say, coming from the tip of a rocket. If you're sitting on the rocket, the tip is stationary with respect to the shock is stationary. It may not be a normal shock, but then there are ways that you can translate what we learned for a normal shock into what we can say for a oblique shock. You have to kind of change your coordinate frame and rotate ourselves in that direction, the shock normal direction. So in real life, I think it's possible to have a situation where it is fairly stationary, but it is slightly different.
So if you had no turbulence and you had just uniform flow,
Yeah.
you can actually figure out what the speed of the shock is.
Yes.
Right? Is it the reason why you can't just go to a traveling frame of reference and be stationary because the turbulence itself will change the speed of the shock? Is that why?
Yes. So I think if there's no turbulence, it's fairly okay. If there's no turbulence, simple flow coming in, this uniform flow, the shock is actually, the solution is known.
Right. It's an analytic solution.
Analytic solution. So if you specify those solutions as your boundary condition, you will have the shock just exactly.
Right.
Now, when you have turbulence, some of the energy is contained in the turbulence, so it changes those conditions. Those what do you say, the values upstream and downstream. Downstream values will be changed. So to be precise, that you have some pressure, temperature coming in, and now on top of it you have fluctuations. What pressure you get after the shock has now slightly changed. So that is what causes it.
So that's why you need this sponge.
Exactly. So we have to kind of damp some of those things and then make sure that we have a control to make sure we don't know what is the final system pressure. We don't know the boundary condition. So we adjust that to make sure the shock is stationary. Okay. Question? Yes.
How do you set up the shock initially at t equal to 0? Do you just give the profile
Yes.
like a step?
Yes, we just give a profile.
And you develop the steady state homogeneous turbulence separately.
Yes.
You give this step,
Correct.
and you just put it in there with
We just feed
velocity
it.
and
We feed it in plane by plane and it goes through this. Yes. Okay. We have done some of these simulations. Although much of the work that was done previously by our collaborator at University of Maryland, lately one of our PhD students picked up the simulation techniques and done a lot of the simulations in-house, in-house in the sense in India, let's say. It's a big simulation, finding computer time is not easy when it runs for weeks and so on. But we have got good results from that, and some of the results I will show are from our simulations. Okay, so this is the setup. We are solving compressible Navier-Stokes equations, means mass, momentum, and energy equations. We are assuming perfect gas. And the numerical method has to be fine-tuned in such a way that it captures the turbulence adequately, it captures the shock wave adequately, because shock wave being a discontinuity is a bit of a challenge to reproduce in a numerical simulation. Where you have a finite number of grid points, so you can actually only reproduce discontinuity which is as sharp as the grid resolution itself. So there are extensive grid refinement studies, a lot of work goes into these things before we get final results. And okay, that's pretty much what I want to say. Let's move on and see what we get after we put in all the hard work and do some of these simulations. A typical result is like this, where I'm plotting what's called a terminal kinetic energy. We take the fluctuations in velocity, u, v, w being the three directions, and we construct a kinetic energy out of it. And what I'm plotting here is kinetic energy as a function of x, where the shock is somewhere near x equal to 0. What is not very clearly visible is that there is a slight decay in the turbulence kinetic energy before it hits the shock wave. And that is natural. When you have a box of turbulence, there is no external forcing, turbulence will decay. The fluctuations will get damped because of viscosity. So you would see a slight decay of turbulent kinetic energy, and then when it hits the shock wave, something dramatic happens. These values go super high. This gray region is where the shock wave is there, but the shock is this discontinuity, almost like a discontinuity, very thin, but it keeps oscillating over a finite region. Where, as I said, the shock wave responds to the turbulence coming in and doesn't stay exactly thin and fine, normal planar anymore. It actually moves around a bit. Over a period of time, in time average sense, it covers a finite thickness of region. And in that region, we find very super high values of this turbulent kinetic energy. Well, in some ways, it is probably expected that if you have a surface which is changing your velocity and you try to measure the surface going back and forth, you will get not very high fluctuations. It may not be quite turbulence. It's because of the shock motion it's happening. Okay, so that is one thing that we see, and we try to neglect in the sense that we can't really. It's an artifact of the shock wave, shock oscillations, not quite the turbulent fluctuation that we are interested in. So we kind of go past it, and then we see what's happening right after the shock region, this shock oscillation regions are over. That is, we come out of the gray region, and we see a trend like this. The thing to notice here is that there is a decay of turbulence finally after some time, but initially there is some non-monotonic, there's some kind of a transient there. Okay. Transient, and then it comes to a peak. After the peak, it decays. So the decay is understandable because finally turbulence, there's nothing to sustain the turbulence, will decay. But the effect of the shock wave is to first make increase in the intensity from 1, which is normalized here, to whatever, 1.3 for example. Then there is this transient which happens because of some energy exchange, I will come to that, between pressure and acoustic and fluctuations and velocity fluctuations. And then this peak is always seen in the simulations. So this peak happens to be a remarkable point to say that I can use this to say how much turbulence got amplified from 1 to maybe 1.3. That peak is very clearly visible in all our simulations, in everybody's simulation, in all direct numerical simulations.
Is that not a function of Mach number though?
It is a function of Mach. So what I'm trying to say is that I'm going to show the effect of Mach number. How much it goes up depends on Mach number, but at every Mach number you will see a peak value. Okay, that's kind of a signature of this interaction. Okay, there will be a dip and a peak, and then followed by another decay. Fine. Okay, so let's move on and see what else do we get from these simulations. Here is what I'm plotting as the called Enstrophy, which is nothing but vorticity. The way we define the kinetic energy using velocity fluctuations, we can take the vorticity fluctuations in x, y, and z, and define a quantity which is like square of sum of squares of that, and we call it Enstrophy. That's like it's like the intensity of vorticity. How fast are those eddies rotating in some ways, no? Again, we have normalized with the value of 1, and now we have plotted 3 different Mach numbers. And it shows that higher the Mach number, higher is the amplification. So the shock wave is essentially increasing the vorticity in the flow, in those eddies.
So these Mach numbers are upstream Mach numbers.
These are all upstream Mach numbers, yeah, absolutely. So whenever we assign a Mach number, we're saying that what's the upstream Mach number, higher the Mach number of upstream flow, higher is the shock strength, higher is the jump in pressure, temperature, density across it, and higher is the effect of the shock wave. If you say that the shock wave is going to compress the flow, it will compress more when the Mach number is higher. So that's the way we are looking at it. And we'll see that the compression of the shock wave essentially is generating this very high vorticity. The interesting thing also is that if you look at it a little bit closely, you can think of vorticity in x, y, and z direction. So x direction is, let's say, this way, which is normal to the shock. So the shock wave treats the flow differently in x direction than it treats it in y and z. Y and z are what are called the homogeneous directions. Nothing is changing, it's periodic, and as if it extends to infinity in y and z. But the x direction is special. X direction is where we have high gradients, no? And the compression is happening in x direction. So if you have a vortex, imagine a vortex that is, if this is the shock wave, the vortex is aligned like this, the vortex axis is this way, is rotating counterclockwise, let's to be positive. When it goes through a shock wave, it gets compressed. And if you have a vortex which is getting compressed because the cross section is decreasing, you start spinning faster. It's just angular momentum conservation. Okay. So that is what is happening for transverse components of vortices. The shock wave is actually making them spin faster in some ways. But if you have a vortex which is axis along the shock in x direction, not much happens to it. Because the compression doesn't change its cross section. And this thing is visible in simulations. It's very much there in our analytical theory, which is when we come to it. Of course, after the shock, all of these gets mixed up and get balanced out. I mean, they all kind of interfere with each other. But at the shock, the interesting thing is that the transverse vorticity is amplified dramatically. And that transverse vorticity, if you think about those eddies of turbulence, are now spinning faster, rotating faster. So it gives you higher turbulence intensity. Fluctuations are higher, everything is higher. Okay. Yes.
I thought it's interesting here that there is no peak.
Very good point. I want to tell you that this is asked as here there is no peak like what we had for the thermal kinetic energy, going to almost like infinity. Because vorticity depends on the gradient of velocity. It also depends on the asymmetric gradients, if you think about it, it's a curve of velocity. So then a shock wave is like a divergence of velocity, if I'm making sense. So we should write it down. Shock wave, if x is this direction, we have a shock wave. U is the direction, u is the velocity in this direction. A shock wave has very high values of this gradient. This does not contribute directly to the vorticity. Vorticity depends on the other gradients. If we say vorticity is this, is U and V are the velocity components in x and y. I think the signs are correct. So the shock gradient does not contribute to the vorticity. So we don't see that very high peak, interestingly.
And also that other small peak is not.
It's also not there. That's also very interesting. Let me come to that.
Okay.
It's the effect of acoustics which does not interfere with vorticity now. We'll see that in a second. So when we come to theoretical framework, we can analyze a lot of these things from what's happening inside. That's the fun of it, you know. Okay. So we looked at turbulent kinetic energy in terms of velocity fluctuations. We looked at vorticity fluctuations. Next thing we will see is what happens to thermodynamics in terms of pressure, temperature, density fluctuations. Remember that what we took before the shock, the box of turbulence we generated, we said we did not have too much of, almost negligible amount of pressure, density, temperature fluctuation, mostly velocity fluctuations. In some ways it represents incompressible turbulence. Okay. So at the shock, here it is, again very high values of these fluctuations. Again, it's in a similar way that if you have the oscillating shock, which is changing the pressure, if measuring at one point will give you very high fluctuation when the shock moves around with it. But the other interesting point is that this pressure density, all the thermodynamic fluctuation variances that we have plotted here, they get very high values at the shock, and then this has this rapid decay. And which is kind of a bit different from what I would, if I go back in this. Here the decay is mostly gradual, a bit sharp, but mostly gradual. Whereas if you see a very different kind of decay that you see in the thermodynamic variances. This was one of our things that we studied recently, and again I will come back to it. Yes? So what we're doing is we're running the simulation on a grid. We have turbulence coming in, shock wave, all of that is happening. The simulation is computing the values of pressure, temperature, density at every point. And then we are calculating statistics at every point. So let's say we have the pressure as a function of time at a given point. So we would take that and then look at the time average value, subtract that value, and then what we are left with is fluctuation. So then we will take the fluctuation, compute an RMS, and we'll plot it as a function of x. So at every point that we do, we plot it as a function. Does that answer the question? Yes.
Is there a fundamental difference between the way all of these three rise up in the same slope, but all of them decay in a different way?
Yeah. So So I would say that there is really, well, maybe there is, but this rise I would say is kind of artificial, not really about turbulence. It's because of that. Maybe it's because of the shock motion. That's why they all have the same thing. The downstream one, this rate at which they're coming has some physics to it. So that's why they're different in some ways. In fact, we will show that they're actually related by isentropic relations. So maybe you can even derive or kind of calculate the slope difference in their decay rate. And so that way maybe it is true, which I have not thought about now, but I think it's possible that all the going up are because of the shock motion. The single dynamics, the shock dynamics determines all of them. So that means that slope is related in some ways, or almost, maybe even same, I don't know. But they also go to a very high value. On the downstream side, they are actually very near the shock. Some of these fluctuations follow isentropic behavior. So that's where the slopes are different, but they are also related. Okay, very good, excellent. So this is the three, we have studied many more aspects to it, but I showed three different things: velocity, vorticity, and thermodynamic field. Now let's see what we, so then what we do is we try to understand why it is happening this way and how we can use it to our benefit. And that brings us to the kind of theoretical analysis that we do for this problem, and try to go after what's happening inside. To do that, the first thing I would like to show is called linear interaction analysis. It's a theoretical tool, a framework that was developed, as I said, long back. It builds upon what what's called Kovasznay modes. It's very it's possibly you've seen it in other contexts as well. Kovasznay's analysis showed that if you have turbulence, weak turbulence, not very large amplitude turbulence, you can decompose it into 3 modes. One being vorticity, second acoustic, and third entropy. So, and there's some analysis that goes with it. It says the vertical mode is mostly velocity fluctuations, the acoustic mode is dominated by pressure fluctuations, isentropic pressure fluctuations, and the entropy mode is temperature fluctuations without any density, without any velocity and pressure fluctuations. So some of those mathematics is well done in those papers. The way it helps us in this context is that you can actually think of the problem of turbulence going through a shock wave in the form of waves, many waves. If you decompose the upstream turbulence into Fourier components, let's say, each wave hitting the shock will generate 3 waves. In the sense that we say upstream turbulence is only vertical. That was our problem. We said we don't have any thermodynamic fluctuations, so we have only vorticity waves upstream. Once we Fourier decompose it, it has a large number of vorticity waves at different wave numbers, different angles. Take one of them, make it interact with the shock, it will generate the 3 waves that Kovasznay has proposed, and you can actually work out the wavelength, the angle, and the amplitude of these waves just by paper and pencil. And this forms the basis of investigating what we see in DNS to understand more about what's happening inside. Okay, so we take this and then we actually look at the shock now more carefully. Here is a magnified view of the shock wave. It is, this middle line is like the mean position, which is, if it was not disturbed, it would have been at that point, nice planar shock. When it is oscillating or unsteady, we say that we are going to do a change of frame of reference, coordinate frame, from xy to something like x1, x2, which is now sitting on the shock wave. We look at the problem sitting on the shock wave. And we also transform our velocity from uvw to u1, u2, u3. The important thing here is that when we shift from the, let's say, lab frame to the shock frame, we have to look at this quantity which we call as psi. It's a function of y, z, and t in this framework, x being the shock normal direction. It determines the shape of the shock, essentially, as a function of y and z. And if we take a time derivative at any point, it will tell us how fast the shock is moving at that point. And if you take a y or z derivative, it will tell us how the shock is curved, how much is inclined relative to its mean position, which was exactly there. Okay, very simple mathematics. Once we do that, and we make an assumption that all these quantities are small, okay, that's of course the basic starting point, we can actually do this transformation, drop some of the second order terms, keep on the first order terms in the fluctuations. What it shows is that the velocity transformation brings in u prime. If u prime is the fluctuation in the fluid velocity, xi t is the shock speed. The difference between the two is what's important to us, because now we're sitting on the shock wave and looking at the flow coming at us. And you will see this u prime minus xct coming many times in our when we try to understand the equations and the physics. When we go to the second and third components, there is a angular variation of the shock that comes in, again when we have linearized the problem. I will for the purpose of this presentation, stick to this part and then try to explain to you what we are getting out of it. Let's look at the next thing. So I'm trying to tell you the building blocks of this analysis. There are a lot more detail that is there in these papers. What we're doing is that we take the what we call as the elementary interaction, a single wave interacting with the shock, generating multiple waves, okay, which can be solved analytically. We start with spectrum of turbulence, upstream spectrum, what's the distribution of energy as a function of wave number, and then we integrate it for all these single wave interactions, and what we'll get downstream is the turbulence statistics. So as if turbulence coming in was split into component waves. Each wave was made to go through the shock wave, and because we have made the assumption of linear, dropping non-linear terms, we will get the output for all of these interactions, individual wave interactions. Then we integrate over all those outputs to get the downstream turbulence. Yes.
The wave number of the distorted shock,
Yes.
so is that related to the incoming?
It is. It's exactly it. So in fact, with the length scale in this, if you call this as elementary interaction, the wave number of the upstream wave and its orientation, these are two important things. That determines how the shock will be, what will the wave number of the shock wave.
So your small amplitude assumption
Yes.
is really an assumption on the kind of input waves you have.
Precisely. In fact, when I say shock, small amplitude is actually for u prime, v prime, what is coming in. Yes, precisely. Yes. That relates to the shock will also be deviated by small amounts from its mean position. So that we can imagine that there will be some limitation of this as its amplitudes go higher. But in fact, we'll come to that if time permits, that the limitation comes in the range of transonic, as we call it, Mach number equal to 1, not at very high Mach number. It is quite interesting in its own way. Okay, so this is the framework that we're working in. We will study both the single wave interaction and also the 3D integrated form of this to look at what we can gather out of it. And let's see what we have here. This is the first set of results. If you do that an analysis and you get you try to predict how much turbulence will be amplified across the shock wave, it turns out it's a function of the shock Mach number. Mach 1 being a very weak shock, there is no shock wave beyond less than Mach 1, and as we increase Mach number, the shock gets stronger and stronger. What we have plotted here is a different way of showing the turbulent kinetic energy and its ratio of downstream to upstream. So this number on the y-axis shows how much, by what factor it got amplified. So for Mach 2, if we say it got amplified by, let's say, 50%, if it is about 1.5 and so on. So what this line is from our linear interaction analysis, LIA, if we call it for short. What we have plotted, all the symbols are from direct numerical simulation. So now how do we look at it? It's quite a mess and quite a clutter. Because it happens so that linear interaction analysis neglects all nonlinear interactions, as we expect, as we said. It neglects viscous effects. It assumes it's an inviscid scenario. It's an infinite Reynolds number. Because of these differences, qualitatively things matter, but when you want to put the two things on the same plot, it's quite a bit of a challenge. So let me quickly tell you a few things instead of all. These crosses are those peaks. The turbulent kinetic energy had a small peak, as I said. That is the peak which is most prominent and is easy to pick that value. And you put it here, it is lower than what the linear theory showed. Because linear the DNS had viscous dissipation. Turbulence is, okay, let's go back and look at it. So this peak happens slightly away from the shock wave. So if the shock wave amplified turbulence and then it started decaying. So by the time the peak happened, some of the decay had already happened. So your value would be less than what the theory would be. So naturally what people would do is, why don't we just extrapolate this back to the shock wave? Okay, and see what it gives. It turns out that it takes you to these symbols. Quite close, getting closer. In fact, the additional ways of processing it, looking at how much dissipation happened during that time, and can you back calculate that and take it out of your energy, and so then you can get these pluses, which is fairly close to the line. So overall, the point is that the theory is getting something correct, even if not exactly matching with DNS, because the two things are doing slightly different things. One is in the scenario of inviscid no decay, whereas the other one has continuous decay of energy. So overall, I think this is fairly satisfactory to see a plot like this, where the symbols are fairly bracketing the line.
So why are there multiple, so for example, the crosses?
Yes.
Why are there multiple points at the same Mach number.
Good point. So what this is because of, there are three parameters. Mach number is only one of them. The turbulent Mach number is the second parameter. So you can actually really keep one constant and vary the other. Or you can change Reynolds number in the small range of DNS, whatever DNS allows you to do that. So that is the variations. Yeah. Okay. Question? Yes.
What's the y-axis again? I missed.
Y-axis is the factor by which turbulent kinetic energy is amplified across the shock. So if you assume you normalize everything to 1, what value would you be getting after the shock?
So what is the definition of, this is not, so you had mentioned that you could normalize it with the peak that comes after the shock, right?
I said we will measure the peak as our level of amplification. So what I would do is, if I go back, the peak would be my value. So in this case, I will normalize with the value before the shock. And the peak value I get, let's say it is about 1.3, I would put that 1.3 on that plot. Okay. Yeah, exactly. That's what.
So that is what it is.
That is what it is. It's written in a slightly different way because I take it from different papers. Sorry about that. But yeah, so RKK is the Reynolds stress, the trace of the Reynolds stress, which is twice the turbulent kinetic energy. They're connected. I think it's yeah.
So that plot,
The other one?
yeah.
I didn't go to that.
So according to the linear analysis, it was kind of saturating after a certain Mach number.
Yes. Something about 3 or so. Yes.
But like increasing the Mach number will also make the non-linear effects prominent. Is that why? Because it is the linear analysis is sort of saturating.
In fact, I would say that so our understanding is that the shock, the saturation will happen in even a non-linear scenario also. That is our understanding because the shock, if you have the shock wave and let's say you measure the strength of shock in terms of how much pressure rise it gives, how much compression it does, it also saturates in the limit of high Mach. So all these quantities saturate at high Mach number. In fact, I would say this is actually an aberration. There's something quite right with this aberration. Usually all of the things will saturate, many things saturate. Anything else? Okay. Here's the other one, which is actually far easier to interpret. What we're plotting now is vorticity, what we call it is the vorticity fluctuations in all three directions. We defined an Enstrophy, which was like energy, but using the vorticity fluctuations. So in some ways, this quantity represents the strength of vorticity in all three directions taken together. Again, we have normalized it with the upstream value. So this number on this y-axis says how much it amplified by what factor, and the line is LIA and the DNS symbols are DNS. So apart from this, which has separate explanation, the match is quite good. And in fact, what we say is that it's actually because of how you can extract the data from DNS. If you go back to vorticity, there was a very clear peak, and this was not cluttered by the shock oscillations. There was no dip and going up, no transient, very clear peak was there. You pick this value, put it on the plot, your LI line almost goes through. So again, LI is actually capturing something, the basic part is capturing quite well, we thought, when we saw that. There is a bit more interesting thing about vorticity in terms of what I explained earlier, the circular vortex becoming squished a bit because of compression. But there's also Baroclinic effects. I think we're going a little slower compared to what I thought. So, but if somebody is interested, we can come back to this. Okay, the next thing is, let's look at this. So here is what's called propagating and decaying regimes, which is an interesting artifact of this interaction. And this explains why there's a dip and going up. The transient is explained by this. So what we do here is, again, this is something from the papers in the 1950s, and they have done a quite good job. We have borrowed it from them. Now, what we're showing is that we have this wave. Let's say we have a shock wave, and there's a wave that comes and hits. Now, as we said, the wave imposes something on the shock as well. The shock starts oscillating. So the y direction of the wave has the same speed of the shock wave. Both have the same behavior. They're kind of in sync. Okay. So now there's a wave propagating on the shock. If you are sitting on the shock and moving with the wave, then essentially you are stationary. You don't see the wave. It's not oscillating anymore. It's just a stationary wave on the shock wave. Does that make sense? If that happens, essentially you're changing coordinate frame. And you're actually moving up with this wave. So essentially you're putting a vector down. Now your upstream flow, which is coming horizontal, now will come at an angle. In terms of shock wave, we switch from a normal shock to an oblique shock. It's not very easy, and I probably need a lot more time to explain it, but just take it from me. That what happens is oblique shock, when you have an oblique shock, the flow is now coming at an angle. Mean flow is coming at an angle. And interestingly, I've not shown all the details, the wave is stationary, the shock wave is stationary, everything is a steady problem. It's a very interesting special case. It becomes a steady problem. At any point, nothing is changing with respect to time. Even though everything changes with x and y, but that is steady in time. For that problem, every point in the shock behaves as a source of disturbance, and depending on the angle of this, of the incoming flow, you can actually have different kind of wave pattern behind the shock. Why that happens is that for oblique shocks, depending on the shock and the flow angle, the downstream flow can be supersonic, sonic, or subsonic. So if it is supersonic, then the sound wave that you're generating will form a pattern like this. The flow is carrying this wave and the wave is expanding. It's a sound wave. If it is sonic, the expansion is kind of limited and all the waves coalesce at that one point. The speed of the flow and the speed of sound are matching. This can actually be worked out nicely if you have a piece of paper. And if it is subsonic, you don't have any coalescence. So as it turns out that this is a situation where sound waves propagate along these wave fronts. Acoustic wave fronts are generated and these acoustic wave fronts propagate, take the energy away. In this case, the energy doesn't quite add up and all the energy kind of quickly decays. So this becomes a decaying regime. If you have this angle psi is the angle of the incident wave. You can do the geometry and work it out. If the wave was coming more like this to the shock wave, it will be in this regime. If it was coming more oblique, this upstream wave, it will be more of this kind. So this is a characteristic signature of this problem. And this
just one question. When you say decay, you mean the drop of turbulence as I move in the streamwise direction?
yes, exactly.
So it's not decaying in a
Time.
viscous sense. I'm not losing
Yes,
energy.
it's not
really the
dissipating.
drop off.
Yeah. It is decaying. You're right. It is decreasing as it goes away from the shock wave.
Okay.
And that is that dip in the profile that we see. So it's a bit tricky to understand. It took us quite a while to actually read the paper and work it out many times. But the basic crux is that you have to change your frame of reference if you want to study this phenomena. And then you can actually work it out that depending on the wave angle of the upstream wave, you can get these three different kind of pattern of waves. The acoustic wave follows this pattern. If you look at Kovasznay modes, the vorticity and the entropy waves are not affected by this so much.
If the upstream Mach number is very high, are you biased to one of these scenarios?
Good question. So this is called the critical angle, and you can calculate the critical angle as a function of Mach number. It depends on the Mach number. Doesn't vary so much, I think. Doesn't show a very large variation. It's in the range of 60 to 65 degrees, if I'm not wrong. But I have to check on that. But I think we are not seeing a very strong bias. In fact, something else happens where as the shock gets stronger, other modes become more prominent. So this effect we don't see so much.
I see.
Yeah, even if the angle doesn't change so much, but the effect becomes smaller. Its signature becomes smaller.
I see.
Yeah. Okay. So this thing is what gives us the. Let me go back. Well, let me see how to connect the dots. Let's do this. When I say that the acoustic energy drops quickly as we move away from the shock, this is what happens in this scenario. This shows up in the form of these drops. We can actually work it out and show that it's an exponential drop away from with x being the distance from the shock wave. It can be worked out again from this analysis. And the thermodynamic fluctuations, pressure, density, temperature, at least for Mach numbers up to about 2 or 2.5, shows this very characteristic exponential drop. It turns out that in this range, the acoustic mode of out of the three modes of Kovasznay, the acoustic mode is dominant. So all of these things are following the acoustic mode pattern that we have studied in the transient. Okay. Here is another place where this acoustic transient makes a difference. That is in the form of heat transfer. Now, how do we define heat transfer? We take the velocity fluctuations at a point, take the temperature fluctuations, and now I've written that in terms of internal energy fluctuation. There's a factor of the specific heat. If you correlate the two, it tells you how the velocity fluctuations are transferring or taking temperature with it. If this correlation is high, it means that there's a lot of energy transfer because of the turbulent mixing. If it is low, the other way around. So we look at this quantity, in fact there's a name for it, it's called turbulent heat flux or turbulent energy flux. That's the name technical. So we look at this term from the DNS data and from LIA. So we have, this is the shock location at x equal to 0. These two dashed lines are from DNS, which show the shock oscillations. Upstream, we don't have much of temperature fluctuation. This quantity is almost zero. There's no net heat transfer. Downstream, we have this peak value followed by a decay. The line is from the linear inviscid theory, and these symbols are from DNS. Two different Reynolds numbers are plotted. And the thing to note is all of them have this peak, a positive peak in heat transfer. The DNS goes down, drops after the peak because of viscous nonlinear effects, whereas LIA, the linear inviscid theory, gives you a constant value. So this part is expected. We have not accounted for the decay in the theory, so we can't reproduce what we see in DNS. But this part is fairly close, at least qualitatively, definitely matches up. And turns out when we do investigate this peak and coming down is because of those acoustic mode, the decaying energy. There's some amount of energy transfer between the different modes that gives you this. And if you're looking at heat transfer, this peak is important because that tells you what's the maximum amount of heat transfer that can be induced by the shock wave. And initially I said that when you have shock waves in these rockets or aerospace vehicles, they can result in high heat transfer with the shock wave ranges. So this is a quantity we are very much interested in, the peak value, what it is and how much can be predicted, and can we predict using this, can we predict the heat transfer that happens on a rocket?
So did this actually suggest that linear theory is a safe bet for design?
Linear theory is a safe bet. I think we can say some of these features are quite well predicted. The problem, next thing is that how do you relate this to the real scenario? That is what we, yeah. So I think as far as capture the physics, we'll say linear theory is quite good in this case. It cannot capture what is happening here, accept it.
No, but in terms of peak temperature,
Absolutely.
you're much safer going with linear theory. The nonlinearity is not
yes, shooting it higher or making it higher. Absolutely. I would totally agree with that. So it's quite a safe bet in terms of if you want to use it to predict something. So that is exactly what we have done. Can we take these results from the linear theory, validate it with DNS, and then use it to make a CMT prediction of the real thing? That is where our thing went. How are we doing with time? Oh, I'm already at 40 minutes. No? More than 40 minutes. Wow, okay, I should speed up because the real thing is still yet to come. Okay, so this is the real thing. So we have gotten quite a bit of understanding and whatever else we said. How do we use this for modeling and simulation? This is a picture from one of our simulations where there is a shock wave and other stuff happening in some real kind of scenario. This can be a deflected flag of a rocket or something like that. Okay. Maybe I'll skip a few things, but let me go a bit faster here. We want to predict how much. Maybe I should go to heat transfer because it's a bit short of time, right? Yeah. So let's go to heat transfer. Let's skip a bit. Sorry about this. Let's look at this for a second, okay, and then we'll go to heat transfer. So this is a picture we are familiar with: a shock wave coming from adjacent side of the vehicle, impinging on this surface, where it has a turbulent boundary layer. This is the scenario which is what we call think of the inviscid scenario. When we have the boundary layer, we actually have flow separation. There will be a reverse flow because of a shock wave is an adverse pressure gradient, and flow can go backward. It can separate. The boundary can separate. It turns out that this vortex, that small bubble that forms there has important implication for heat transfer, because the flow goes over it and then that kind of impinges at this point what we call as detachment. That is the point where we find the highest heat transfer. So the question is, can we predict that heat transfer? Also what we are showing is this one shock actually splits up into multiple shocks and many more things happen in this flow than just a simple scenario like this. So when we do CFD of this, we are able to capture the shock structure, compare it with experimental shear images and all the other things that goes on behind it. I'll skip that for a second. It turns out that if we take the linear theory framework and we write simple energy balance across an oscillating shock wave, you can actually get an estimate for the heat flux, turbulent heat flux that I talked about, that we plotted earlier. And we can actually write it in terms of Reynolds stress, this shock speed, and the shock strength in terms of R, which is density ratio, for how much compression does the shock produce. This was a very interesting and a very simple expression for predicting the peak heat flux behind the shock. We could not use it directly because there was no way to put it into a CFD code, because most CFD code use what's called a Prandtl number for turbulence. We had to convert that into a turbulent Prandtl number using some modeling of assumptions and all that stuff. But you can see some same form comes in this framework. And then when we put this value of turbulent Prandtl number, what is generated by the shock wave, because of the shock wave, turbulent Prandtl number takes this value which can be predicted based on the shock strength, R, that is the parameter, which depends on upstream Mach number. We take that and then we apply the same flow field where there's a shock wave coming and then there's really complex multiple shocks and all that. So we identify the region where shock wave is and apply this correction on those points. Prandtl number can be varying depending on the shock strength locally. And then when we look at actual experimental data, here is the point 0 being where the shock impingement happens. The flow actually responds to the shock a bit ahead of it, changes from its undisturbed heat transfer value on the flat plate slightly higher, and then goes much higher where the impingement and reattachment happens. If you don't use the corrected Prandtl number, you would get somewhere here. With the corrected Prandtl number, you are much closer to the experiment. And of course, this is one of the cases. Now we are running, this is actually very recent work that we have come across. This paper came out earlier this year, and we are running many more cases where we can show this kind of trend is happening. It's very exciting actually for us, because for many years, people knew that heat transfer cannot be predicted using conventional methods like this for shock when there's a shock wave. And people had proposed some very elaborate ways of tackling it. Now, the way that we could use linear theory to come up with this one small algebraic form which fits into 5 to 10 lines of CFD code actually makes a big difference. So with that, we are probably down to 5% of error compared to 50, 60, 70%, sometimes even more than 100% error. And let me stop by saying that this does make a difference when you have, as I said, when you have multiple rockets boosters together and can have heat transfer at these points. There's actually history of these kind of problems in what was called the X-15's flight in 1960s, where there was something here which caused an impingement and there was a damage to the aircraft, and the aircraft had to, I think it had to eject some of these extra pieces it was carrying. It had an experimental engine which caused this problem, and it had to eject the experimental engine, I think. But the aircraft landed safely. So these kind of things do happen in flight. You have to take care of it. You have to fly safely. And some of our predictions will make it easier and better to get the estimate of heat transfer and have your protection, adequate protection for this. I think we are pretty close to the end. So what I'm trying to say here is summary slide, that we do spend a lot of time looking at basic problems like this, homogeneous turbulence, normal shock, and more like toy problems. Spend a lot of time understanding the physics, but then we take it all the way to develop models and apply to implement into CFD codes, numerical challenges and all this stuff, to simulations where it makes a difference to ISRO or DRDO, whichever projects we are working on at times. And I think with that I would stop here. This is another slide, and with this picture of our students and collaborators that we have worked. Thank you so much for your attention.
I think there are many questions and we are kind of run out of time. So let's have the question and answer session outside.
Sure.
Thank you.